All right. I think we're okay. And happy Wednesday. Happy 8 a.m. Hopefully it works. All right. Well, anyway, I got the syllabus posted. Homework 1's posted. The lecture notes and stuff are posted. Homework 1, we haven't covered anything, so don't. But I mean, you're gonna have to start soon. But it's up there. All right, and let's start our first lecture. We'll try to cover as much as we can. If we have to do the last few slides on Friday as well, or something, or maybe I'll record like a little 10-minute supplemental video to get this. But I want to just talk a little bit about just kind of the basics of this idea of modeling. I remember, when I came to grad school in statistics, people were talking about statistical models. And I probably went through like my first year kind of just unsure of what a statistical model was, but everybody used this term so regularly, I was like afraid to ask, like, what is a statistical model even to start with? And I don't know if any of you feel like this. But hopefully we'll clear up a concept of what is a statistical model here. So statistical models and models or whatever is a big part of machine learning, and so this is what is okay. Is this okay if I'll just leave it like this? All right. So this is just the Wikipedia definition of machine learning. I don't know, it might have updated, but this is pretty good enough for me. It says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. The idea is we're going to try to fit a model to some data. And, it says without using explicit instructions, relying on patterns and inference instead. This concept of machine learning, there is a lot of it in that the machines kind of learn and kind of teach themselves, but ultimately people still have to make decisions. People still have to kind of do some teaching and training of the models regarding how do we specify the model. But once you kind of specify that, a lot of the decisions, a lot of the kind of parameter weights and things that are up for tweaking in the model are guided by the data, guided by the algorithms instead. And when we allow the algorithms to kind of make these decisions, we say the machine is learning, okay? What is a statistical model? Here, this is a model airplane, all right? And in the way that this is not a real airplane, it's a simplified representation of an airplane. A statistical model is a simplified representation of kind of a real-world process, right? So if you think about stuff that happens in the real world, okay, there's something that happens that generates data, right? So for example, we wanted to gather data on how tall you are, all right? So let's say that's the response variable. What goes into determining how tall each person is? A bunch of factors, right? There's like genetic things, nutrition things, environmental stuff. All kinds of things go into how tall someone ends up being. A statistical model is a simplified representation. And so a very simple model could just be like, oh, well, you know what? People's heights just are random and they're centered, that follow a normal distribution, okay? And that like kind of ultimately generates some distribution that's somewhat reflective of probably data we would gather. You could further tweak that and say, okay, well, maybe if we say, we look at gender or sex, we could say, one gender has a mean of this and another gender has a different mean and things like that. We could take into account other things, and we can say, all right, if taking into account race or ethnicity, we could further tweak certain aspects and stuff. But ultimately, it's just a simplified way of how do we generate our data, right? So in the real world, what determines the values that get counted in the data? There's a complicated process. And what we're trying to do is we're trying to find some simplified mathematical or statistical representation of whatever process or whatever system it is that generates that data, okay? So that's what I've defined as a statistical model, okay? So a statistical model often includes simplified versions of the relationships between variables, okay? And there might be, in the real world, there might be hundreds or thousands of variables, okay? And generally our models will contain, a subset of variables, perhaps like the quote-unquote most important ones. And there's always going to be some kind of leftover error term that just says, even though we've accounted for these 5 variables and we've really tweaked the thing, we know that the actual value that we record in the real, in the real data is not necessarily going to be exactly what we predicted, okay? And what we're trying to do is we're trying to create a model so that that amount of error is generally as small as possible. We want our predictions to match the real world data as closely as possible, but of course, we can't get it perfectly. This quote, "All models are wrong, but some are useful," is something good to keep in mind, okay? We have generally and very broadly speaking, we can say statistical models kind of fall into kind of 2 categories of use. One is we can use models to make predictions, and that is how we measure the validity or how useful a model is by we say, okay, what did the model predict and what is the actual value? And we compare those things and we say, this model is making better predictions, therefore it's the better model, okay? We can also use models to kind of gain understanding of the relationships between variables. This one, the predictions, the accuracy of the predictions are, obviously we want accurate predictions, but sometimes understanding the relationships is more important. So if you think about linear regression, and I'm assuming you all took 101A by now, when you have that, you have these kind of, your prediction is a linear combination of your predictors. And so, when variable x1 goes up by 5, okay, then your prediction goes up by beta 1 times 5, right? And that's, and we understand a relationship, okay? And we can say, all right, when you change this variable, your prediction changes by that. And so we start to learn some of the relationships between some of these things. A lot of times, what kind of model we choose reflects which of these priorities are more important. And I would say, in general, machine learning, kind of this field of machine learning, highly prioritizes the accurate predictions over understanding the relationships. Okay. We have a textbook. Did I point out what textbook we have? There is a textbook, and it's called A First Course in Machine Learning. And I apologize, I don't have, I try to generally pick textbooks that are free for you guys, but I could not find a textbook that I liked. So this is the textbook that we're using, Our First Course in Machine Learning, and you'll need it, okay? Oh, look, the AI is talking to me. Okay, but anyway, this is a data set that they're using. They look at the Olympics 100-meter dash, track and field event. And they look at what is the gold medal winning time. And I think this data is a few years old, but this is kind of what the data looks like. So, kind of the Olympics in its current form has been going on since around the 1900s. 1896, I think, was kind of the first, and every 4 years we've been, we see these things, and this is the winning race time, and what we see is that over time, the winning race time for the 100-meter dash has been getting faster and faster and faster and faster. Okay, so this was 2000, 2004, 2008, 2012. So this data is already about 10 years old. But this is what we see, and the question is, all right, what's going to happen in the future? But can we build some kind of model that forms a relationship between the year in which the event was held and the winning race time? And that's what we have. Okay, and so just kind of a simple statement to summarize the data that we saw in that previous slide was that race times have gotten faster over time. Okay. And if we know the year of the Olympic Games, we can try to predict what the winning race time was. We can create a linear model, all right? And a linear model, kind of the key idea of linearity here, implies that the amount that we're going to adjust between our prediction remains constant throughout the entire data set. So if we predict the time improves by 0.05 seconds, from 1920 to 1924, then we're going to predict that the race time improves by the same 0.05 seconds between the year 2000 and 2004, right? So it doesn't matter if we're talking about going from 1900 to 1904 to 2000 to 2004, whatever prediction we however much it improves there. Obviously this can't hold on forever because by the year 2100 to 2104, we're saying it's gonna keep getting faster and faster and faster, and if this holds true, eventually we will have negative race times, and that's just not possible, right? This linear trend can't hold on forever, but perhaps in the range of the data we've collected, it works, right? And so how do we fit the model? Okay, fitting the model, ultimately when we're talking about fitting a linear model, it comes down to determining two values. What is the slope and what is the intercept? These are the two kind of little knobs you can adjust on your model. One is you can change how steep that line is, okay, positive slope, negative slope. You can adjust the intercept, and so you can imagine like the worst Etch-a-Sketch, right? Where, one knob adjusts where your line goes up and down, and then the other knob adjusts how steep your angle is, or the slope of your thing. And you're you're twisting these two knobs to try to get your model to fit the thing, okay? So fitting the model comes down to kind of estimating the model parameters. In a linear model, we have two, okay? Other models, all right, that we'll talk about later on in the course, there's different parameters to adjust, okay? And now for the linear model, we already know the answers, right? You took linear regression. We know how to calculate the slope. We know how to calculate the intercept for the best fitting line. But I want to take a step back and just say, kind of taking from a machine learning approach, we have to define what does it mean to have the best line, okay? And so we can have different definitions for the best line, and how we define that word best in terms of the best fitting line is very important. And how you define that's carried out through kind of what we call the objective function. So for linear regression, our objective function is the residual sum of squares. And we say the best fitting line is the model. The line is going to be your slope and intercept that minimizes this total squares of residuals, right? Where we define the residual as the difference between the actual value and the predicted value. And we say, let's take the difference between the actual value and the predicted value, actual value being y, predicted value being y hat. We say, take that difference, square it, add them up for all of your data points. And I think this is familiar, right? We're all familiar with this. And we say, let's find the slope and intercept, which will change what our y-hats are, and we want to try to find the slope and intercept that's going to minimize this thing. And so this is our objective function. Because we're trying to minimize it, other words we use for it are the loss function and the cost function. Oh, I forgot I need to give you view quiz answers too. Okay, so and that's just because you generally try to minimize your losses, you try to minimize your costs. So that's why we call it those things. A lot of machine learning problems have some kind of objective function that we are either trying to minimize or maximize, okay? And therefore, a lot of machine learning algorithms, we can just think of them as optimization problems, finding the set of values that will give us the smallest this, or finding the set of values that give us the biggest, value of our objective function. And so we're going to start here. This is where we will start as far as framing our objective functions and concepts for machine learning. When you look at the textbook, it uses a kind of notation that's a little bit different, okay? And so so when I presented the sum of squares, and here this is going to be the mean squared error, I said, we have the actual value is y, and the predicted value is y hat, okay? As far as the textbook goes, it says, the values that we're going to predict from the model are basically what the function outputs given your x values. And our model has two parameters, the slope and the intercept, okay? And just more generally, we call these the weights of the model. So the letters they use are weight 0 and weight 1. That's the intercept and that's the slope, okay? And you can think of more models having more parameters or a whole bunch more weights, and so a lot of times we see the letter W for the different weights that appear in our model. And so this is f of plugging in value xn given weights w0 and w1 is going to be our predicted value, okay? And then the value that we are trying to approximate, the actual value, is given by tn, our target, okay? T for target. This is the value that we are trying to aim for, okay? So our mean squared error, okay, is can be expressed as y minus y hat squared summed up over n, or we could say tn minus f of xn, given our weights, take that difference squared, sum them up, and divide over n. Okay, so that's the textbook's notation. So if you see all of these different letters, that's what's going on. Okay, and a very common measure that we also see is the RMSE, the root mean squared error. Okay, RMSE is basically you just take the square root of this thing, and this just, if you have units, okay, if you're measuring like the target is $20 and you're trying to make a prediction and you predict $19, okay, you have a difference of one square dollar if you do this sum, and I don't know what a square dollar is. And so you take the square root mean squared error, we'll turn it back into your original units, okay? And the parameters that optimize the root mean squared error are going to be the same parameters that optimize the original mean squared error or sum of squares errors. Okay, so anyway, the linear model is we have an intercept, we have a slope. These are the two weights that we are trying to determine, and this is what we want to do, right? So if we say this is our function, okay, we can plug that function into our loss function or our objective function, and we get this is what we have, the actual value, target minus what we're predicting, which is W0 plus W1 xn. We're taking that difference and we're squaring it. And we want to minimize this, okay? And I think, do you do this in 101A or 100B or 100C, or you do it in all of these things, or you're also gonna do it here, okay? All right, so I'm gonna kind of just go through this really quickly. But basically, we're going to say, what is the intercept? What is the slope that we're going to pick? Okay, these, the fitted values, so our W0 hat and our W1 hat, are the values of W0 and W1 that minimize this thing. That's what this argmin thing is. Find the arguments that minimize this quantity, okay? And so basically, how are we going to do this? Well, one way is you can do this with calculus, right? And so in calculus, you got this function of two variables, W0 and W1. How do you find this minimum thing? You kind of take your partial derivatives and you set those equal to 0 and you solve, and things like that, right? So we could do that, okay? And is that how you solved it? All right, you did partial derivatives and you solved. Okay, and that's why we said you need to have what, 31b as part, or 32a as part of your thing. Okay, so prerequisites, they're all good. Okay, let me give you. I'll go ahead and give you your first two view quiz answers. Letters A and B. Letters A and B are your first two view quiz answers for today. A and B. Okay, so we'll pretend that we did this, and these are the solutions that you get, okay? So I skipped a bunch of steps. The full details are in your in the textbook, but I'm also going to say you've probably seen this before, and I feel okay jumping to here, okay? So this is what you do in calculus. Partial derivatives, you set them equal to 0, you solve, okay? Did you solve the thing also using linear algebra? Have we done that yet? I think that comes in 100C. Yeah. Okay. All right. So, so we like linear algebra, maybe. Okay. If it's been a while since you've taken your linear algebra course, or if you were like me and you never took linear algebra as an undergraduate student, and you came in and you were lost. I wish I had this, but anyway, I had a lot of catching up to do. This 3 blue, 1 brown, one of the best channels on YouTube has an excellent playlist on linear algebra, and I strongly recommend it to everybody. Even if you love linear algebra, just seeing some of these visualizations are great. And so what we're going to do is we're going to do the same thing, okay? Basically, we're just going to solve the problem in another way using linear algebra. We're going to say, hey, how do we figure out the W0, the weights of W0 and W1 using linear algebra rather than the partial derivatives, okay? So we're going to say our weights are gathered into this matrix W, including our weights W0 and W1, and our observation, our single observation x sub n, okay, our nth observation x is going to be the value 1 and the actual value of xn, okay? And the function, right, which is basically our intercept plus our slope times xn, can now be expressed as w transpose xn, right? We can multiply w and xn, and this is what we would get, okay? So we can express our function as this linear algebra operation. What if we want to do it for the entire matrix of x, okay? Well, now I have capital N observations of x, and so if I take each, the first observation, x1 transpose is going to be 1 and x1, and the second observation was 1 and x2, and so on and so forth. Now I have a matrix that has n rows and 2 columns, okay? So we will say that, and then our values, our predicted values will be big X times W, right? And then our target values, basically the values we're trying to predict, our Y's, or our T's here, can be gathered into this. And we could say our loss function is going to be T minus XW transpose T minus XW. Now, let me kind of just show how we got that here, okay? So we have our X matrix is n rows, 2 columns, and if we do X times W, okay, big X by W, so this is n by 2, this is 2 by 1. When we multiply this, we get a column, n by 1 values, And all of these are going to be our predictions, right? All of our predictions, W0 plus W1 times X1, W0 plus W1 times X2. These are going to be all of our predictions, okay? And so this is going to be X times W. Now, sometimes when you deal with matrices and whatnot, it can be confusing. Do I write XW or do I write WX? Because we're accustomed to this multiplication commutative, is it the commutative property? Where you can do like A times B is the same as B times A, and that's fine when you're dealing with scalars, okay? But you can't do this with matrices. So always, I strongly recommend that you always get in the habit of writing your dimensions underneath each of these things, right? And so you do X is an n by 2 matrix, W is a 2 by 1 matrix, and you know that the number of columns in this matrix has to match the number of rows and the kind of the matrix next to it for it to multiply out, okay? And that way you will avoid the problem of doing W times X instead of doing X times W, okay? So when you do matrix multiplication, the kind of these inner dimensions, the number of columns over here and the number of rows over here, they have to match, otherwise it's not gonna work. And so anyway, we get XW, which is n by 1. So these are our predicted values, XW, and here just this is how we can do it in R. These are my X values, and I want to create my matrix X. So I'm going to just bind a column of 1s with X, okay? And so X becomes 28 rows, 2 columns, okay? And then W, I just have a column matrix of 1s, 2 rows, 1 column, and I could say W is 2 by 1. And then if I do X times W, this is the matrix multiplier in R, that says, okay, that works. You get 28 rows, 1 column, okay? If I try to do W times X, right? If I try to do W times X over here in R, I get an error. I said non-conformable arguments. Non-conformable arguments is basically saying the number of rows, number of columns in this matrix doesn't match the number of rows in the next matrix, and that's a fairly common error that you will encounter when doing matrix multiplication. So just know that when you encounter this message, non-conformable arguments, that means your matrix dimensions don't align, and maybe you have to switch things around and just kind of go down on a piece of paper and say, all right, what are the dimensions? And you go, oh, okay, this is why something's not working out. Okay, anyway, if I do T minus XW, I get my residuals, right? The target value, our first target value minus my first prediction, the second target value minus my second prediction, and I do this for all n predictions. So these are my target values. This is n values, 1 column, right? So this is just a column of residuals, and now I want to get my squared residuals, okay? Squared residuals will be done by doing the transpose, T minus XW transpose, times T minus XW, right? So when I transpose this column of residuals, it's going to be 1 by n times the column, which is n by 1. And so if I do a 1 by n times an n by 1, I'm going to get a 1 by 1, which is going to be all of these values, right? The first value times itself, so plus the second value times itself, plus the next value times itself. So we're going to get basically the sum of all of the squared values. All of these things squared becomes just T minus XW transpose T minus XW. And this is one of the beauties of linear algebra, is that you can get rid of summation signs. You can just do T minus XW transpose times T minus XW, and that takes care of the summation. The matrix multiplication includes the summation in there. Okay, and then we just say, okay, well, the loss function, which is our mean squared error, is just going to be 1 over n. Okay, and so we could see when we do this, we get a 1 by 1 scalar value, and that's exactly what we want. When we plug in our values, our loss function, we just want a single value for our loss function. We don't want to have to deal with like 7 values that we have to simultaneously shrink or something. We just want to, how do we shrink our one loss function here? Okay, so, well, how are we going to fix this? Okay, well, let's expand our thing, right? So I got T minus XW transpose times T minus XW. And so I don't know if we remember all of our kind of linear algebra rules, but when you apply a transpose to a thing, you get, to the things, you can just apply it that way. When you apply a transpose to a product, you can transpose each of the each kind of component, but you have to reverse the order of those things, okay? So now I have T transpose minus W transpose X transpose times T minus XW. And then, we kind of do, first, outer, inner, last to when we multiply kind of these terms. And so you get T transpose T, T transpose XW, W transpose X transpose T, W transpose X transpose XW, okay? And I wrote the dimensions underneath each of these things because we know that the answer has to be a 1-by-1 scalar, okay? And we want to make sure each of these terms are all 1-by-1s, okay? And so just to kind of make sure everything works out, I wrote the dimensions underneath of these things, and indeed all of these multiplications work out 1 by n times n by 1, 1 by n times 2 times 2, 2 by 1, and all of these things, they all work out to be this. Here, I can combine the T transpose XW with the W transpose X transpose T. Are these words coming out of my mouth? Okay. So I can combine these two things because these are transposes of each other and they are scalars, right? So you can kind of combine them into this thing. So this is what we have. And so we could say our loss function can be written this way. T transpose T 2 times W transpose X transpose T plus W transpose X transpose XW. And this is our loss function. And what do we want to do? Okay, so this is like, I can combine those things. Now we want to minimize our loss function using vector calculus, okay? So now that we have defined our loss function in terms of matrix notation, we want to say, all right, let's find the value of W that minimizes this, okay? And so how do we do this? We're going to use vector calculus, and we're going to say, all right, what is basically the derivative with respect to W? We're going to set that equal to 0, and we'll solve for W, okay? That's what we're going to do, okay? So we're going to take the derivative, but this time we're taking a derivative with respect to the vector W. We're going to set that derivative equal to 0, and we're going to solve for W. And so this involves doing a little bit of calculus using vectors. And so derivatives is kind of the limit as this goes to 0. And we have kind of the multivariate equivalent, which is the gradient, okay? And here, our output is a single scalar, okay? It's a single real numbered value. That's the loss function. It's just one number. But the input is a vector. We have n values going in. So here our vector, we have two values, okay? So the input of our function is two values in two real numbers, okay? And so we want to find kind of the gradient here, okay? This is this upside down triangle, okay? Like an upside down delta. This is known as nabla, okay? And this is kind of like your derivative, or the gradient of the function, okay? And so the input is basically, so if you have the input vector, which has, let's say there's n terms in your input vector, the gradient with respect to W is basically the partial derivative of f, with partial derivatives to W, and it basically becomes a vector of partial derivatives. And so it'd be the partial derivative of f with respect to W1, partial derivative of f with respect to W2, so on and so forth to the partial derivative of f with respect to Wn. So this is basically what it means to get your gradient, okay? So here I've got two terms in my W vector. I've got a W0 and a W1, and so my gradient is going to be basically a vector with two terms, the partial derivative with respect to W0, the partial derivative with respect to W1, okay? The derivative represents kind of the slope of your tangent line. The gradient represents points in the direction of the greatest rate of increase of the function, and its magnitude is kind of the slope of the graph in that function here. These are some handy terms to use that we can use when calculating gradients here, Okay, so if we have this term W transpose X, and we're saying what is the gradient of this with respect to W, the gradient is X. If you have X transpose W, so all of these things need to be are 1 by 1 values, right? If we do X transpose W, what is the gradient with respect to W? It's just X. What about W transpose W? This is kind of like W squared, okay? It's not exactly that, but you can kind of think of it that way. And so what is the gradient with respect to W? You get 2W. And then if you have a square matrix, so here I've got C being a 2 by 2 kind of square matrix, we get 2 times C times W, okay? And so so here's just kind of a quick explanation showing like some of these some of these things. So if I do W transpose X, we can see W is W1, W2, and X is X1, X2. So if I do W1, X1, and W2, X2, you know, what is the partial derivative with respect to W1, and what's the partial derivative with respect to W2? We can see the partial derivative of this with respect to W1, well, this part we can ignore, and this will just become X1 over here. What's the partial derivative of this thing with respect to W2? It's just going to become X2. So this thing, the partial derivative with respect to W1 is going to be X1, and the partial derivative with respect to W2 is just X2. And so this would be our result, and we can say, oh, that's just X, right? X1, X2, it's just X, okay? Similarly, if you have W and W transpose W, you get W1 squared and plus W2 squared, and what's the partial derivative with respect to W1 and partial with respect to W2? You can see you get 2W1 and 2W2, which is just 2W, right? And you can derive all of these other ones if you want, but you can also just say, all right, let's just take your word for it, okay? And so, I kind of went quickly through this, but maybe we'll squeeze it in. Okay, let me go ahead and give you your last view quiz answer for today. Last view quiz answer is the letter E. E as in elephant. E as in elephant is our last view quiz answer. Okay, so we left off and we said our loss function is this thing, right? So T transpose T and W transpose X transpose T and W transpose X XW, and I put kind of the scalar terms 1 over n and 2 over n and things like this. And we say, let's take the gradient of the loss function with respect to W, okay? So here, I don't have any W terms here, so this is just going to zero out, okay? But it's a matrix, a 2 by 1 matrix of zeros. What is this, okay? Basically, this is W transpose times, if you think of what is X transpose T, this part over here is just some kind of vector. And so the gradient of this with respect to W is going to be just X transpose T. And X is 2 by n, and T is n by 1. And then over here, I have W transpose XW. Okay, so this is kind of your square matrix C. And I've got a W, it's kind of like a WCW, so kind of like this thing here, W transpose CW. And then we get 2 times that square matrix, X transpose XW. All right, and so this is what we have, and this is a 2 by 1 matrix. This is a 2 by 1 matrix, and so our gradient of the loss function with respect to W is a 2 by 1 matrix, and this is what we have. All right, so that's what we want. That's what we get. Is it okay if I just go a couple minutes over? And so what we want to do now is, so we say, here's our gradient with respect to W. Let's set this equal to 0, and let's solve for W. So here I've got 0 is equal to this. I can multiply both sides by 2 over n, okay? And then I add this to over here. I get X transpose T is equal to X transpose XW, okay? We don't have division in linear algebra, but we can multiply by inverses if we have like a square matrix. So I'm going to get rid of this X transpose X. To get W by itself, I'm going to multiply both sides by the inverse, X transpose X inverse. And so I do this, and I get X transpose X inverse times X transpose T is equal to, and then this part becomes the identity, and I get just W, right? And I think maybe this looks familiar, okay? X transpose X inverse, X transpose T is equal to W, so therefore the value of w that is going to minimize our loss function is going to be x transpose x inverse x transpose t. And that's kind of where we are. We haven't covered anything brand new, and this is, you're going to cover this again in 100C. But this is just kind of, again, the big picture here is we said here is this function that we want to minimize. In our case, the sum of squared residuals. And we say, well, how do we minimize this? We're going to tweak our weights, and we're solving for that. And so today we kind of did this analytic approach, and we'll start here, and we'll keep this in mind, and we're going to kind of move forward. A lot of stuff we're going to be working in linear algebra. So if you need to brush up on linear algebra stuff, this first week is a good time to do that. But yeah, we'll end here for today. Thanks for being patient with all of the technical stuff this morning, and we will see you all on Friday.